So when we apply this concept to photoreceptors, here's how it's going to work. So the receptive fields of photoreceptors, it's essentially light. Okay, if light is hitting a photoreceptor, it's going to fire. Okay, now photoreceptors connect to ganglion cells. Here's how this works. So we've got a bunch of photoreceptors. Okay, these are just a bunch of rods and cones, right? They are just a group, a little neighborhood here. And this neighborhood of photoreceptors um, gives input to this ganglion cell. Okay, so there's your ganglion cell, and this is the ganglion cell's receptive field. So now let's translate that receptive field into something like this, right? So this is the receptive field, and this is the center of the receptive field. So now I want you to imagine this whole scenario. Oh, it kind of looks like a little person. This whole scenario over here. Okay, so ganglion cells have their receptive field composed of photoreceptors, and what happens is it's set up in a center surround situation. So a ganglion cell will either be an on-center cell or an off-center cell. So what this means is it will fire when light is on the center of the receptive field, okay? Or it will fire when light is off the center of the receptive field. So let's check out this on-center cell first. Right, so here we are. This is the same thing. Imagine all those tiny little photoreceptors in here. We put light on the center of the cell. Okay, so we put light on all these photoreceptors. Okay. There's no light on the surround. Well, it's an on-center cell. We have light on the center. The ganglion cell is going to fire. Now, if we have light on the surround and no light on the center, the ganglion cell is not going to fire because it's an on-center cell. It likes light on the center. If we don't put light on any of these photoreceptors, the ganglion cell obviously is not going to fire. If we put light on all of these receptors, the entire receptive field, now we have light on the center that it likes, right? So that's excitatory, and light on the surround, which it doesn't like, that's inhibitory. So you're going to have a response, but it's not going to be as distinctive a response as you get when you only have light on the center, which this ganglion cell prefers. Okay, now the same is done just sort of in reverse for an off-center. So an off-center ganglion cell is going to prefer light off the center of its receptive field, right? So here we have light on the center. It doesn't like that. It doesn't fire. Here we have light on the surround and not on the center. This is its preferred situation, so it fires really well. Here we don't give any of these photoreceptors light, no light in the receptive field, cell doesn't fire. Here we give all the photoreceptors light. Now we have the same thing, right? We have light in the area that it likes and light in the area that it doesn't like, so we have a response, but it's weak. Okay, so this is how photoreceptors feed into ganglion cells and are the ganglion cell receptive fields. Okay, now from the ganglion cells, we go to the optic chiasm, which you know about, and from there we go to the lateral geniculate nucleus. Okay, which we talked about before. This is a little bit more of, so a little bit of a diagram of what the LGN is sort of set up to look like. I'm not going to get into it too specifically, but I just want you to take note of the organization. Okay, so the ganglion cell axons, right, we know that they form the optic nerve, and that travels through the optic chiasm. Okay, and some of these axons, right, just like we had photoreceptors, some of these axons, photoreceptors feed into a ganglion cell receptive field. Well, some of these axons feed into the LGN receptive field. Okay, so if you think of this as the lateral geniculate nucleus, so if you imagine that it's this area right here, this layer of the nucleus is getting information from these axons, right? So that is this layer's receptive field. Now we have We have right and left visual field information that travels to different layers of the LGN. Okay, it's very organized. So this is right, this is left, this is right, this is left, this is left, this is right. Okay, and it's going to be the same thing over here. This is just a stained cross section of the nucleus in the thalamus. Okay, so this is actually what it looks like. This is not like a schematic drawing. This is actually what it looks like. So let's have a look at how this works in practice. Okay, this is called a Hermann grid. And this is actually a demonstration of your receptive fields at work. Now, the big thing to remember is that we have larger receptive fields in the periphery. Okay, so ganglion cells that take in information from photoreceptors closer to the fovea of the retina, they're taking in information from a lot less photoreceptors. Okay, the further out you get, the more photoreceptors are feeding in information to one particular ganglion cell. Okay, so you have larger receptive fields in the periphery. Now, what you should see when you look at this grid, essentially, is that there are black dots. Like it seems like the intersections are shaded in with black dots. But when you go to look at one particular intersection, like straight on, you won't see the black dot. You are only going to see the black dots in your periphery. Now, why does this happen? So here is what your receptive fields look like in the fovea. Okay, they're small. So when you're looking straight on at one of these intersections, okay, this is the receptive field layout. So now notice how much light is being projected onto one of these guys in the alleyway versus onto this guy here in the center. Okay, so these guys, they're completely lit up, right? The whole receptive field is lit up. And in the center, the whole receptive field is lit up, which means that there's no difference between what I'm seeing here and what I'm seeing here. Okay, so when you look straight on, you don't see any difference. Everything looks the same color. Now, what happens in the periphery? So you're still looking straight on here at this particular spot, okay? So now let's take a look at what happens in the periphery. So in your periphery, the receptive field at the intersection looks like that, and the receptive field in the alleyway looks like that. Okay, now I want you to notice these are on center receptive fields, right? So light in the off center is going to be inhibitory. So this is all inhibitory. This is the inhibitory response of a cell in the alleyway. Now, this is the inhibitory response of the cell in the intersection. As you can see, there's a lot more inhibition going on here in this receptive field, which means that this area is going to look darker than this area. Right? So that is how receptive fields sort of play out in real time. And this concept stretches all the way back to the visual cortex. Okay, so this is a primary visual cortex receptive field, okay, of one neuron in the primary visual cortex. Now, what you can see here is that this receptive field likes light in the center, okay, and it does not like light in the surround, okay? So that's what the receptive field looks like. Now, if you take this and you compare it to this diagram over here, which one of these bars of light most matches this receptive field? And it's obviously going to be this one. Now, this guy, so if we have light going in this direction, what we have now is light covering this area, right? So, okay, this is what you have for activation, is this area right here. Okay. Now, when we look at this, we can say, all right, well that's going to be like this. Okay. And now you can't see it because my drawing sucks, but you get a larger area of activation that way. Okay, so that's why you're going to get some response here. You're going to get not really a lot of response here. You're going to get major response here because cells in the visual cortex also have preferences and their receptive fields have preferences. All right, so these preferences, okay, so when we map the preferences of all these cells in the visual cortex, we find that things are super duper organized. Now, this is a little bit more complicated than I decided I wanted to get with you guys. So let's just say from the lateral geniculate nucleus, we have things passing to the visual cortex. And if you map out the receptive fields of the visual cortex, you find these really nicely organized orientation columns. Right? So the receptive field of this particular area of cortex is shaped like this. This one is shaped like that, the preferential receptive field, right? So all that to say that it's a very highly organized system. There are some redundancies that help preserve the system. And okay, so that is vision at the level of the brain. So going from the eye to the brain, how we get that information to the visual cortex so we can then perceive that incoming information. All right, so that's it for vision. I will see you in the next topic, which we're going to be talking about audition, but we'll first have to talk about sound. I'll see you there.